Okay, in the first podcast, we just introduced the gas laws in terms of pressure and how we measure pressure. We talked about manometers and barometers. Well, now what we're going to start doing is using those units for pressure and combining them with other variables that we can measure gases with. And in this first podcast, we're going to cover what we call Boyle's law, and it deals with the relationship between pressure and volume. So basically, if you have a system, and let's just say it's a balloon, if you were to increase the pressure on that system, in other words, pushing down on it harder, what's going to happen to the volume? And then what we'll do is do some calculations with that volume. The one thing I do want to emphasize before we get started is the idea of pressure on the inside of the system and on the outside of the system. First of all, on the inside of the system, pressure is caused by the gas molecules hitting the sides of the containers. If those gas molecules hit the side of the container more often or with greater force, you're going to increase the pressure. If there's fewer collisions with the side of the container, you'll decrease pressure. Now, when we're talking about Boyle's law, looking at the relationship between pressure and volume, what we're speaking about is the outside pressure on the system. And that's important to realize as we're talking about these systems. Okay, what we want to do is look at an example of what Robert Boyle may have done to first discover the relationship between pressure and volume. So what he did was a series of experiments. In other words, in the first experiment, the system had a volume of 117.5 cubic inches, and at that volume there was an outside pressure of 12 inches of mercury on the system. Now remember, we rarely use inches, but since inches is used in this diagram, we'll just stick with that for right now. So then what Boyle did was, in a second experiment, increase the pressure on that system to 16 inches of mercury, and notice that the volume went down to 87.2 inches or inches cubed. He did a third experiment by increasing the pressure a little more, measuring the volume. Another experiment increasing the pressure more, measuring the volume, etc. And what Boyle noticed was that there was a mathematical relationship between volume and pressure. In other words, if he took these two values and multiplied them, he got an answer. When he did that with the second set of data from the second experiment, multiplied them, he got the same answer. So as long as he was keeping temperature constant, as he increased the pressure, the volume went down at a constant rate. So he came up with the relationship volume times pressure equals some constant. Now usually we write it P times V is equal to K. So in a system, whatever you do to the pressure, the volume is going to respond. So if you multiply those two values together, you're going to come up with the same value. So Boyle's law can be written mathematically, PV is equal to K. If we go back to our experiment here, in our diagram, if we call this pressure 1 and volume 1, and the second experiment we call it pressure 2 and volume 2, if volume times pressure is equal to K for the first experiment, and the volume and pressure of the second experiment is equal to K, what we have is V1 times P1 is equal to K, which is also equal to V2 times P2. So what we can do is rewrite that P1 times V1 is equal to P2 times V2, essentially because they're both equal to K. So Boyle's law can be written mathematically two ways. PV is equal to K, or P1V1 is equal to P2V2. This is the version that we'll normally use. The idea being, if we had a gas at a certain pressure and volume, if we were to say increase the pressure or decrease the pressure, we could then calculate what the new volume would be. That's what we'll do in the following example problems. do want to emphasize though, when we're talking about pressure, as you can see, we're talking about the outside pressure on a system. So here we have a piston or a cylinder with the outside pressure pushing down. If you increase that pressure, you're going to decrease the volume, as you can see. So if we were going to do this problem here, we would use our formula. P1V1 is equal to P2V2. We would use our first pressure, 5.6 times 10 to the third pascals, times the volume at that pressure, 1.53 liters. Set that equal to the new pressure, 1.5 times 10 to the fourth pascals, times our new volume. So what we can do there is solve for V2, and we would get 0.5712, and our unit has to be consistent. Our unit would be liters. Okay, let's take a look at another example using another apparatus that we will use. These are called syringes, and I'm sure everybody knows what a syringe is in terms of a shot that you get at the doctor's office. Well, syringes, bigger ones, can also be used to take various measurements with pressure. So here we have a certain amount of pressure being pushed down on this system, and the pressure is 1.68, and the unit there is atmospheres. That's a little hard to see. So if we use our formula, P1V1 is equal to P2V2, our initial pressure, 1.68 atmospheres, the initial volume, 7.0 milliliters, set that equal to our new pressure, 4.4 atmospheres, and let's assume we don't know the new volume. We do, but let's assume we don't, and let's calculate it. So do the calculation, and what you find is V2 is equal to 2.67 atmospheres, which rounds to 2.7. Okay, these exercises can also be done with words. You don't need the visual to solve the problem. So let's take a look at this one. We have a sample of helium gas that occupies 12.4 liters. Now what you'll see me do is write the variables as I read them. So liters is a volume unit. So I'm going to say I have a volume equal to 12.4 liters. That's at 23 degrees Celsius, so that's a temperature unit. So I'm going to write 23 degrees Celsius at 0.956 atmospheres. Atmospheres is a pressure unit. So I'm going to write pressure, 0.956 atmospheres. What volume will it occupy? In other words, I'm trying to find the second volume, so I'm going to put a question mark there, at 1.2 atmospheres, so that's my new pressure, as the temperature stays constant. So my temperature is not changing, so I'm just going to cross that out. So now we've got P1, and let me write this here, P1V1 is equal to P2V2, and then you can just plug in your values. Your P1 is 0.956 atmospheres. Your V1 is 12.4 liters. Your P2 is 1.2 atmospheres. And we're solving for V2. When you put that into your calculator, you see you get V2 is equal to 9.88 liters. Let's take a look at another one. You've got a gas with a pressure of 300 torrs. So right away, pressure is 300 torrs with a volume of 45.6 milliliters. So V1, 45.6 milliliters. What will the volume be in milliliters? So right away I'm just going to write V2 if the pressure is changed to 450 torrs. Now the one thing you want to be careful is is that your units are consistent. If we had been given that in 450 atmospheres, which would be a really high pressure, we would have to convert that to torrs before we do the problem. So in other words, your pressure units have to be the same and your volume units have to be the same. So if we set this up, 300 torrs, that's our P1, times V1, 45.6 milliliters, equal to P2, 450 torrs, times V2. So we solve for V2, and we get 30.4, and again, remember, our unit is milliliters for volume, so we put our unit in there. Let's take a look at one more problem. We've got a balloon containing 500 milliliters of gas, so let's write our unit right away. Volume, remember, milliliters is a unit of volume, with a pressure of 304 kilopascals. So pressure, 304 kilopascals when it's on top of a mountain. Once the balloon is carried off the mountain, the pressure changes to 500 kilopascals. So now our new pressure is 500 kilopascals. The temperature inside the balloon stays constant, so we don't have to worry about that. What would the new volume be? So again, you can see all you're doing is taking that formula P1V1 is equal to P2V2 and solving for the unknown. So our pressure, 304 kilopascals. Our initial volume, 500 milliliters. Our second pressure, 500 kilopascals. We're solving for V2. When you do the calculation, you get 304 milliliters. Now, don't get confused here. You might be thinking, well, hold on, it didn't change. Your initial pressure was 304 kilopascals, but your final volume is 304 milliliters. Honestly, that's just a coincidence that 304, 500, 500, 304. That's just the way the ratio works out. Okay, that ends this vodcast with Boyle's law. And Boyle's law can be summarized two ways. Pressure times volume is equal to a constant, or we could say P1V1 is equal to P2V2. You just want to remember a couple of things. This relationship works when you're at constant temperature, so let's write constant temperature, and you want to make sure that your units are consistent. So whatever unit you use for pressure here, you want to make sure the unit is the same on the other side, and also with volume. So if you're given an initial pressure in atmospheres and a final pressure in millimeters of mercury, you simply have to convert one to the other before you do the problem. As usual, email questions to Hannon in Chemistry, and we will see you in the next podcast when we take a look at the relationship between volume and temperature.